about the length and time dilation formula. It's actually a mistype here. It's the time dilation formula, and it's actually the length contraction formula. I don't know why I wrote that. It should be contraction. Okay. So here are our two formula, and I'll start with the time formula. Okay. And basically your standard issue, pretty typical explanation is you have to do essentially a thought experiment. Okay. And so what you do is you get this spaceship here. All right. And your typical spaceship that I'm going to do is going to be something like that. You got a guy inside here. And in this spaceship, a beam of light shoots up to the top here. Okay. And this guy has a clock. Okay. And he measures how long it takes for this light to reach the top. Okay. Well, we know that this is distance, right? Right there. And we know that the velocity of light is equal to c. All right. And so we also know that this velocity, equals distance over time. So velocity equals distance over time, or in his case, the velocity of light is going to be the distance that it travels divided by the time at which he experiences it. Okay. And so that's kind of the idea there. We've got some kind of distance, and that's going to be, we'll call that time S for stationary, right? Why are we calling this stationary? Because we've got the event, which is the light moving from one location to another. Those two green dots are stationary with respect to the clock that is measuring that time. Okay. Now, let's take the same spaceship, right, and pretend like it's moving with a velocity, v. And somebody on the outside can see this velocity, right? And basically what's going to happen is, let's say this ship ends up moving from here to here, right? And this is let's say it's got really fast, this ship. Somebody on the outside, actually I'm going to put this guy over here as well. Actually, I'm going to stick him right there. He measures the same exact event, the same light, right? So it's not that we've done this twice. It's the same exact event. Same light moves from there to there. Okay? From this guy's perspective. Okay? And he's got his own clock out here. Right? And we want to sort of put this into a relationship. Well, we've got some kind of distance here. We've got D, right, over there. This, I guess I'll call, I don't know, L for length. Okay. And in terms of this guy's opinion, he knows that the velocity, remember, this is a piece of light still, right? Or a beam of light. It moves at the speed of light for both of these people. All right, that's Einstein's second postulate. The light moves at 300 in a vacuum, or whatever, in a vacuum, we'll say. 3 times 10 to the 8 meters per second for all viewers, right? So, and it's kind of like what we said before. It's, because this ship is moving, it's not that this light moves more quickly, right? It moves at 300. So the speed of light that this guy realizes is L, right? Distance that it travels over the time. and I'm going to call this time moving. Why time moving is because the 2 points in space that are being used to measure the distance that the light travels, they are moving, both of them, right? Both the starting position here, where the light started, and where the light ended, okay? They're both moving with respect to this clock. And so this guy's going to use the TM formula, all right? And so there we have it, okay? Now, don't forget that this is still D, right? In both people's opinions, right? It's still the same distance across the side of one ship, from the ship, sorry, from the bottom of the ship to the top of the ship is still D, and that's the same for both people, okay? So that's something you don't want to forget, is both people observe that distance to still be the same, okay? Now that that's all said and done, we've basically, essentially built a little triangle here, right? Now, there's one other distance that I want to talk about, and that's going to be maybe down over here. We'll make this in purple, and that is this distance here, right? I don't know if that's purple or black, whatever it is. And we'll call that, I don't know, it is C. No, we can't call it C. We'll call that distance A, all right? Now, that distance is basically how far the starting position of the light moved during this whole thing, right? And the only person who can measure that distance is this guy outside, right? And so what we're going to do is we're going to say, well, that distance, remember, is the velocity equals the distance A over time moving, right? And why am I using, what's V? Remember, V is the velocity of the ship, right? So if the ship is moving really, really quickly, this distance A is large. If the ship is moving slowly, that distance A is small, all right? In my diagram, it's a little bit weird because it appears that my ship is actually moving faster than the speed of light because A is larger than D, but that's not going to be true. Remember, A really should always be smaller than D, right? I just happened to draw my diagram badly, okay? Anyway, look at now. I've got basically 3 equations here. This one, right? This one, and this one. And they all lie in a right triangle, okay? And I'm going to now take those distances and put them into the Pythagorean theorem, right? So based on the Pythagorean theorem, you can see that L squared equals A squared plus D squared. Well, L is just C time moving squared. A is just V time moving squared, and D is just C times stationary squared. And this right here is now the relationship between the 2 times in terms of the velocity with which the ship is moving compared to the person outside, okay? And that basically, if you do some algebra on this equation here, you get algebra, you can make it look exactly like this, okay? But I'll do that in just a moment. But I just want you to kind of maybe take a look at this and make sure that you understand what ended up happening there and why TS and TM are where they are and all the D's and the T's and the L's and things like that. All right. So now that we have this relationship, this is a usable formula, okay? But the way that mathematicians deal with this formula is they tend to obviously solve for Tm. As you can see up here, Tm is isolated. So I'm going to take this formula, and I'm going to solve for Tm, all right? So in order to do that, I'll go ahead and pass my thing over here. So I'm going to get C squared Tm squared minus V squared Tm squared plus, equals, right? C Ts, each of these values squared. We can factor out a Tm squared, and then we end up with a parentheses C squared, C squared minus V squared equals C squared Ts squared. I think we were supposed to divide by a C squared before we do this, but we can do that right now. I'm just going to divide everything by a C squared, okay? Both sides, which basically I would write it here, C squared, and divided by C squared. But I can now distribute this C squared back in, and I end up with the C squared here and here, right? It would be more clear if I would have done it in the previous step. Now you'll notice that these C squareds cancel, and this actually becomes a 1, all right? So I end up with the following, right? Oh no, I want green. Maybe I'll just keep with my green theme here. Tm squared equals Ts squared over 1 minus V squared. Here we go. 1 minus V squared over C squared, right? And then I should probably get these things to be a little bit bigger. There we go. There we have it. Oh, now I got to square root both sides. So in the end, I end up with Tm equals the square root of Ts squared, which is just Ts, over the square root of 1 minus V squared over C squared. And there we have it. There is the formula. All right. There it is. Okay. That's pretty cool in the end. And so we'll do a few examples on, I think that's the way that it looks in the textbook. Sure it is. All right. Now, oftentimes, actually, it's written like this. Gamma, I believe, is it a gamma? No, it's not a gamma. Or lambda, that's a lambda I've written a lambda, but I think it is a gamma. And gamma is the other way around. Or maybe it's an epsilon. I'm not sure what this variable is. I'll have to double check it. It goes like this, Ts, right? Which basically you can kind of then say that this little funny y-looking thing is the 1 over root of 1 minus v squared over c squared. Why is this important? This is a number, 1 minus v squared over c squared. It shows up in a wide range of relativistic formulas, okay? Anyway, keep that in mind. Keep that in mind. All right. So now, essentially, what we want to do is I want to basically have y'all go through the length formula. We'll also go through the length formula, the length contraction formula. All right. So this is the time dilation formula. Okay. And then also the implications are here that more time goes by for this guy, okay, than for this guy, okay? More time goes by. The reason being is because the light has to travel further. L is larger than D, right? You can kind of see that L is larger than d. So from this guy's perspective, the light has to travel further than from this guy's perspective, okay? But in order for that all to work out properly, and since light travels at the same velocity, right? So if I move my little arrow thingy here, it's like that's how fast it moved. Here I'm going to do that. I'm going to do so you can see that I did a lot more doot-to-doots in this guy's vantage point, from this guy's vantage point, than from this guy's vantage point. So as a result, you can see that more time elapsed on this guy's clock than on this guy's clock. Because again, the light travels at a constant rate regardless of the viewer, but here it has to travel further. And so the only way to compensate for that or rectify that strange behavior is that, in this guy's opinion, more time actually elapsed, okay? So that would be the time dilation formula. And the sort of the overall encompassing concept is that if you witness of an event that's moving, it will take longer for you. It'll take longer for that event to unfold, in your opinion, than somebody else who's witnessing that event from while moving along with that event. Okay, you kind of see what I'm saying? Another thing that messes people up is that I've called this, guys, to time stationary here, right? Time stationary. I'm going to write that down, by the way, which I didn't do. And then later on, everybody says to themselves, well, wait a minute, this guy is moving, right? Yes, he is moving. But remember, the event that's being observed is the light going from one side of the ship to another, okay? So the event is stationary with respect to the guy holding the clock. That's why when I first introduced all of this stuff, I just told you this guy's standing in a ship watching this, and I said, okay, this is a stationary event, and I called it time stationary, and then no one was really surprised, right? So I was like, oh, that's why I was trying to say that before I introduced the idea that the ship is then moving. And then you say, okay, this guy now is measuring a moving event, all right? So that's kind of the idea. And by the way, in terms of like getting a question right in a Physics 12 course, one of the more difficult aspects of this is determining whether or not something is going to be a TS or a TM, all right? Anyway, let's do the length formula as well. Basically, if you take this time dilation formula and you multiply both sides by length, right? By velocity here. So I'm going to do Tm equals Ts over root of 1 minus v squared over c squared. So just algebraically, I'm going to break out a velocity of the ship. Excuse me. The velocity of the ship, and I'm going to multiply it by both sides, okay? And now, basically, the idea here is that Lm is TSV, and Ls is TMV, okay? You'd be like, whoa, wait a minute, why are those guys switched, okay? Because, let's take a look at this here, all right? So taking a look at this, what we're going to do here is I'm going to take over here a distance. And I'm going to go ahead and stick it right here. All right. And that's the distance between 2 points, point A and point B, right? I'm not even going to write the A and the B down, but let's just say this is A and this is B. This is a distance that's outside of the ship. Okay, taking a look, this guy can go over here and glance at that distance. He can go over there and glance at that distance. Remember what's going on though. This guy is moving by, right? So in this man's opinion, and this clock's opinion, what's going on? Is this distance moving or not moving? From his vantage point, it's moving backwards in, like this, because remember, he's moving this way. So that distance appears to be sort of going backwards. If you remember, think about looking at a tree or something on the side of the road in a car. From your perspective, I mean, we know that, let me just finish the statement. From your perspective, it appears that that tree is moving backwards. So we're going to call this distance length moving from this guy's perspective, okay? Now let's take a look at this guy who's outside of the ship. What's going on with this length from his perspective? This length is just sitting here, and so is he. And it's the ship that's moving by. And so this length here is stationary from his perspective. So I'm going to call it length stationary. All right? Does that sound pretty good? And basically, let's say that length happens to correspond to how far the ship moved in a certain amount of time. Okay? How far the ship moved in a certain amount of time. And so we can basically say that the velocity of the ship, based on the certain amount of time that went by, is that length. Okay. Well, for each of these two guys, they measure a different time. And so, as a result, because this velocity it's basically how far the ship moved in a certain amount of time, it has to sort of correspond to the velocity of the ship, all right? So basically, what's going to end up happening here is this guy, he's going to figure out, well, how far did I move? Well, it's dependent on the velocity of that I have right now, and is how far I moved, which is some length, which happens to be moving outside of from my vantage point, based on the amount of time that elapsed on my clock in here, which his clock in here is TS, okay? Now, this guy is saying, all right, well, the distance that the ship moved is LS here, and it's based on how fast the ship is going. So in his opinion, this guy's opinion over here, he's basically saying that the velocity of the ship should be equal to the length of that the ship moved, LS. Why S? Because it's a stationary length with respect to this red guy down here, divided by the amount of time that went by on my clock, which is now called TM, remember, okay? And so that's what's going on there. And that's why these two formulas are like this. And so what I did then is I just took this TS and multiplied it over here, and this TM and multiplied over here, and I basically came up with these formulas here, all right? And now, basically, if you look at this formula, which is the time dilation formula, and I take the V, and remember I multiplied both sides by V. I did it a little too early in my explanation, but now pretend like I'm now multiplying both sides by E, and look, what's V times TM? It's LS. And what's V times TS? It's LM. So I'm going to go ahead and replace that with LS equals LM over root of 1 minus V squared over C squared. And if you look closely at that red formula that I just wrote, it's equal to this formula right there. Because, well, our textbook takes this and passes this square root over to the other side through multiplication. And so you end up with length motion. So some sort of length or some distance that's moving with respect to a viewer is equal to the length that it would be observed by somebody who's stationary with respect to that length times this square root of 1 over v squared over c squared factor, okay? V being the velocity with which the length is moving with respect to the LM, the guy who's measuring it at LM, okay? And so that's basically that's it right there, you know? So I'll go ahead and click this video on over to you guys, and then in the next one, I'll do several examples here, okay? So here we are. I'm going to click that one over to you.